Right, so I get to talk about computer vision, which is obviously the coolest topic to be working on. If you're stuck working on speech or language, my intention is that you still walk away from today learning about 2 specific techniques that will hopefully be useful to you. But first, I also want to do a little bit of brainwashing. So I describe computer vision generally as having sort of the 3 R's of computer vision: reconstruction, recognition, and tracking doesn't really fit, but close enough. And up until about 3 or 4 years ago, my group and I were working on these classic problems in a very traditional way. The idea was that you try to make everything automatic. You make the computer see what it can do automatically. That's really the only measure of success. And the great thing was that, and is that now, broadly speaking, in these problems, people like us are getting 70% success rates. And you think, well, is 70% high? It doesn't sound that high. Is that all right? And I know you're thinking that, OK, well, he's got the human in the loop in the title, so probably the human is going to come and fix it, get the last 30%. And that's kind of true, not entirely. So first, no, in part. You can already do a lot with 70%. In the old days, you would have a slide showing like the 3 companies doing computer vision. Now, it's thousands of companies, and I don't need to tell you about them. So these are just ones that I'm working with. And with 70% accuracy, you can already make products. You can engineer around some of the limitations. You can have sort of graceful degradation and recovery from failure. So it's possible to do things. The Kinect tracks your body pose. You can remodel people's faces. You can remodel buildings and make video games out of them, or process video. So there are a lot of things you can already do when your vision system only gets 70% running automatically. Obviously, we want to improve the accuracy of vision systems. But the other thing that I want to kind of convince you of is that we want to improve responsiveness. We want vision systems that get better over time and with experience, so that when you run the vision system, it makes lots of correct answers, but then it also makes a mistake. When you point out the mistake, you don't want it to keep making that mistake, right? That's the opposite of responsiveness. So I think there are a few examples of software that personalizes itself, a few, very small number. But in general, spam filters have got the right idea, right? They do something out of the box for you the first time you start using them, but they also listen to you and take your feedback on board and adjust themselves. And I think that's where the frontier is, as Nathan kind of introduced, the bleeding edge. I think that's where we're going next, is systems that really get better, and from very small numbers of sort of corrections, quickly compensate and adjust and customize for you personally, or for a group of users, so that they can get that last 30%, but also just customization. So this is why, whatever your task is, task XYZ, I want systems, whether they're vision or otherwise, that really respond to human feedback and take it on board. So please measure accuracy, by all means. That's very important. You want things that run automatically and accurately, but also kind of look at the mechanical advantage. How much benefit is there as the user kind of pulls in this direction or that direction? So when we talk about the user, I feel I need to clarify, especially because now we're going to talk about the 2 sort of methods that I want to teach you today. Who is the user, right? So my people are over there on the left. We're the ones making the algorithms in the first place and kind of working sometimes in isolation, right? And we think we're clever and we're coming up with stuff and we're trying to make things as automatic as possible. And the nice thing is that when you want to measure your own success, you just do these automatic tests. You just have a training set, a test set, and then you can do everything by yourself. You don't have to interact with people. And I love that. That's great. But sometimes you have to kind of try your systems, and then you send them out into the world, and you realize, oh, OK, well, I'm good, but maybe at the wrong things. So I've got this group in the middle, the operator, and that's where the two methods that I'll present today are kind of targeting. These are the people who need to get a job done. They have an application in mind. They're going to get some dev kits, some APIs. They're going to put the ingredients together and build a system, and it needs to work. And it needs to work a way around the limitations. It has to cope with what the users get confused about. And so it's kind of a messy job, and that's people who know how to program but maybe aren't necessarily sort of in the dungeon with me and my team. And obviously the consumers, that's where the frontier will be. We'll be getting their feedback and responding to their feedback, but maybe that'll be like a year from now when you invite me back. Thank you, by the way, for having me. That we'll show examples of that actually coming to life. So the two methods I want to tell you about, let's just start with the first one. There's a wonderful question. Well, there are a few different neural networks and different ways of training them. Which one did you try? This happens all the time. You have the same task, and you have multiple algorithms that try to deal with that task. And you try method A, and method A works some of the time. Method B works some of the time. And there's not like a clear winner. So which one should you use? So we have this problem all the time. And so we set it up. And it's called example-dependent, cost-sensitive learning, right? So you insert your problem at the top. The problem can be recognizing objects or tracking things or understanding documents or one of those other things related to speech or language that if you really insist. So you have this problem, but now you have algorithm A, algorithm B. You can have as many as you like. You have many algorithms to choose from, and you take your training set and you say, okay, I know the answers for this training set, but I'm going to run each training example through each of the algorithms. I'm going to look to see who's the winner, right? So I take this image and I say, whatever it is I'm doing, I'm recognizing, I'm classifying. Notice I'm not worried about what the task is. I'm just worried about who wins. In this case, algorithm A wins. But the interesting thing that you can do is you can also assign a score, right? You can come up with some measure of success to say, well, it's not just the winner, but maybe it's like the winner by a margin. Like 0.8 is a lot better than 0.3, so algorithm A is the winner by that much. Take another training example. Algorithm B is the winner in this case. But it's only by a hair. And so you kind of note that down, and you realize, yeah, if I ever see images like this, maybe I'm better off with algorithm B, but maybe it's not that important. And then maybe further examples, it doesn't matter, right? There might be some examples where all the algorithms get it right. It's an easy example, fine. So we take all of this training data, and in our case, we put it into a random forest. It doesn't have to be a random forest. And at test time, we come along and we say, hey, look, new image. What's the answer, right? Each algorithm could be run in sequence, but you wouldn't know which one is the winner because it's a test image. You don't know. But the random forest looks at the image, looks at what is seen about and learned about the algorithms, and it says, oh, you know what? This type of image, I think algorithm B is really good at that. So let's listen to what algorithm B says. Let's not even run the other ones. We'll just run algorithm B and use its prediction, because I'm predicting the random forest says, I think it'll give the best answer. So this is the general pipeline. You get your set of favorite algorithms, right? To recap, you pick a feature representation. These days, I agree completely with Martin. It tends to be very often that you take a neural network representation, feed it in, and then you say, OK, I've got some task scores, some measure of success. Apply that, run all the algorithms on your training data, in our case, a random forest, and then you're ready to deploy in the real world, right? You'll still have to compute your feature representation every time on new images. So the buses, you have to compute that. But you won't have to necessarily run all of the algorithms, because you'll just run the one that is predicted to be the best. So for those of you who care about random forests and care about the details, the secret sauce is in the impurity measure, right? So the typical impurity measure says, oh, I've got 3 reds and 1 green, so that's algorithms A, and algorithm B is the minority here. OK, so the impurity is pretty high when I'm splitting the nodes. And the cost-sensitive one, in the case where the task scores are really different from each other, it behaves in the same way. But the cost-sensitive one behaves very differently. If there are 3 red winners here, and one green that's only by a hair. That's like very slightly higher task score. So it says, actually, the impurity is not so bad. Don't bother splitting. So download it, use it. It's good for various topics, not just computer vision. We tested it on computer vision problems, and it works across a whole spectrum of situations, different feature representations, really quite general, and I hope you find it useful. The other task. So remember, we're still talking about the operator. That's our user, right? So the other task comes from the problem that when you have a neural network or some other machine learning system and you need to train it, you need training data. And it's easy to get data, but it's hard to get labels for the data. Now, if you can do unsupervised learning, by all means, do unsupervised learning. That's great. Very frequently, that's not really available to you. So when you have a lot of data and not all of it is labeled, that immediately suggests at least semi-supervised techniques. So I'll kind of just explain briefly what semi-supervised learning is, but the key is that I want to give you a method that will help you cope when you don't have a lot of labels, but you have a lot of data. So in typical supervised learning, you would say, OK, I've got some feature space, two-dimensional in this case. I have 2 labeled examples from class A, 2 labeled examples from class B, right? Whatever the problem is. And then along comes an unknown data point, and it lands here, test data point, and I say, OK, so which class does that belong to? You know, we could play the game, raise your hands, but I think most of you would say, OK, well, it's probably class A, right? It looks like it's closer to class A in this case. So semi-supervised learning comes along and says, well, actually, you didn't give me labels for all these other unlabeled data points, but I know where they are in feature space. Right? That's automatic. And from that, I would say that that data point probably now looks more like it belongs to class B. So there's semi-supervised learning in action, but it does take knowing a few labels. And if your operator, or the user who is building the system and making it, preparing it for deployment to consumers, is willing to put in a few more hours, maybe a few more minutes of labeling time, you don't want them relabeling points that we already know about or that we can classify easily. You want them labeling points that really matter, that really change the model a lot. And so this is where active learning comes in. And active learning, I think, is this great philosophy that some people in machine learning have known about for a while, but it's only very recently that researchers are starting to use it with real users. So, for example, in computer vision, until our paper last year, there'd never been a user study done with real users using an active learning system. They'd always been done in simulation. Well, because then you don't have to, talk to people. So active learning is going to come along, and it's going to say, I'm going to pick a point in this space. I'm going to ask the oracle, so that's the human user in this case. I'm going to say, hey, tell me the label of this point. And then we're going to train the model based on that feedback, and we're going to be able to infer labels. And if the user says, oh, no, I'm still here, I can still label some more data, we'll repeat this, and we'll pick another point and ask the oracle and retrain and so on. So this question of picking another point, that's query selection, right? Which data point unlabeled data point should I pick next? This is the real challenge of active learning. And so I think it is catch me afterwards in terms of like the nuances of this. There are quite a few different strategies to choose from. Maybe in summary, expected error reduction is really quite good. It's a bit of a beast, but once you can come to terms with it, it's really very, very effective. Of course, you have to deal with lots of other issues, and I'm going to skirt around them today. Right? Is the oracle lying to you? Are they telling you? Are they an expert? How long are they going to sit there? And maybe the oracle is changing their mind as they go. So we've encountered this as well, and that's slightly tricky. And also, do they know what they want? This is my favorite bugbear. OK, so active learning, lots of cool things to explore with active learning. But let's say someone comes to you and says, I've got an active learning algorithm. And you say, OK, let me see your learning curve. So this is the way to interpret how an active learning algorithm is doing, or really any kind of learning process where you have machine learning and you're retraining every time you get some more labeled data. Right, so on the vertical axis you have accuracy, right, and we want to be at the top there, and on the horizontal axis you've got user effort. And so the best learning curve is one where the user labels one thing and the curve just shoots up to 100%. The model is perfect, it's accurate, and that's great. If you label a little bit more, though, you should always be getting better. The model shouldn't get dumber the more training data there is, else you're probably overfitting. So this is what we look for in a learning curve. Nice and steep would be best. So for the method that we have code for that you can go and use, we're the black curve at the top. And the thing to note is, of course, we're the steepest and the best, and that's quite good. But the other thing to note is the sort of error bars that you see there. What you're seeing here in red, for example, I'll pick on them. This is the kind of variance that you get depending on the run, because if you're picking randomly, right, each run of the active learning will be different, and it'll make some mistakes at the beginning and get better with time, but there's still some variation. Ours has very little variation. It's very, very tight, and it's the steepest, and it works across a variety of data sets, and that's kind of the other thing to keep in mind when looking at these algorithms, that you want it to not just work on one simple toy data set, but it needs to work across a variety, because presumably you have lots of data and you can't afford to label it all, so you won't know whether things are working or not. So there are a few more details about the algorithm, and so I hope you'll try it out and let us know how it works for you. I want to kind of start to land the plane a little bit. Right? We've talked about two methods that I think you can use if you're the operator. These are, I think, quite generic, but quite cool. Now, we also are working on things that are starting to edge into the zone of the consumer, right, with real users. So these are still prototypes, and they're not really fully fleshed out. But I just wanted to mention them briefly. So we've got this interface we've built with London Zoo, right, to help them annotate images from the seabeds, because this is how they measure biodiversity when they're doing fishing, right? So fisheries are paying for that kind of research. So these are really hard computer vision problems, but it turns out that you really need an end-to-end system. If you're going to do machine learning, it's not enough to just hand them MATLAB code, right? They need the whole thing, the whole pipeline. So they've labeled thousands of images now with this system. The Natural History Museum in London, my favorite museum in the world, so they have millions of specimens. And so we're helping them specifically with their butterflies. They're trying to digitize them before they degrade any further. And so one of the things we've done there is help them. Well, they've already started this process, and that's the great thing. People, like scientists like these, they help themselves, and then you come along and you just supercharge them. So they're trying to label all of these, assign barcodes, and try to make them available online so that enthusiasts can study them and do research sort of from armchair scientists kind of style. So we've made a system there where they can remove them and quickly scan hundreds or thousands and eventually millions of butterflies just by showing them to the camera and pulling them out. And this is all about detection and classifying, and so it sort of has all of the problems all under one roof. There we go. So I'm going forward, but that's not working. There we go. OK, that was the other butterflies. And the last one, video tagger, this new thing. So the paper hasn't come out yet. We have a video that's 3 months long. How are you going to annotate that and do machine learning on that? We have lots of people, biologists and marine biologists, people studying human behavior, people studying mouse behavior. We help them do machine learning on this kind of data set, and that's partly mechanics, but it's also bringing to bear some of these methods that I mentioned. All right, so to conclude, you can reduce the guesswork when you're trying to put together different machine learning pieces. You don't have to commit to one method. You can actually adaptively switch back and forth between them using our example-dependent cost-sensitive learning. Whether you use our active learning approach or other people's, please measure your success in terms of both accuracy and how much effort the operator is putting in. Eventually, that will lead to systems that are nice and responsive. So that's my That's my vision for the future, that we'll have algorithms that really behave like spam filters. So thank you very much.